The Glassboro interpretation can explain and resolve the paradox of the Afshar experiment. In order to quantify wave-particle duality, we introduce two different parameters. These are the particle parameters of which-way information, which is k, and v is the wave parameter of visibility. Together, these two parameters form the complementarity inequality, which is k squared plus v squared must be less than or equal to 1. Which way measures the degree to which we can identify the origin of the particle. If we know where it originates from, we have a max value of 1. But if we do not know its origin, then we have a minimum which way value of 0. Visibility measures the contrast between fringes and interference patterns. If we determine that a particle avoids a certain region, then the visibility will be a max of 1. If it is equally likely to reach any point within said region, then the visibility will be 0. If we take two beams with zero-point fields that cross and end at detectors, we will see a region of interference of visibility equal to 1 at the intersection. As we shoot particles through it, particles will travel in a straight line due to the conservation of momentum. We know if one of the detectors is triggered, then the which way information is 1, since we know where it originates. Since there is a region of interference fringes of visibility equal to 1, there appears to be a violation of the inequality. In the Glassboro interpretation, the particle is the carrier of energy momentum. This means only the particle can be experimentally measured. This also implies that the parameters apply to the particle only. The zero-point fields do not transfer momentum to move particles from dark to light fringes, thus it maintains a uniform distribution, and therefore there is no violation of the inequality. Particles approach the screen in straight lines, however, photons must be deflected from the dark fringes to the light fringes. The force that causes this deflection is the electromagnetic force mediated by virtual particles. In this case, the macroscopic screen will provide transverse momentum, yielding to the formation of constructive and destructive interference fringes. Particle visibility will be maximum, yet we will not know the origin.
When a thin wire is scanned across the beam intersection, an interference pattern is detected. The photon count is a function of position of the wire, where we can see the decrease in photon count with a position. When the wire is at the center of a dark fringe, there is negligible decrease. When the wire is at the center of a bright fringe, the decrease is as large as 12%. This means that there's an interference pattern, so visibility is about 1. In the setup where the wire is at the center, photons that do not interact with the wire pass through, as they are interrupted. This means they have full which-way information and no visibility, since they ignore interference fringe patterns. However, if a photon interacts with a wire and does not change its path, it maintains high which-way information. Since the photon avoids the wire, its visibility is maximum. This violates the complementarity inequality. The Afshar experiment makes this paradox worse, when there's a wire grid placed at the center of dark fringes. Decrease in photon count is minimum in this case. Particles act as if wire grid is not present, so visibility is large. From diffraction calculation, most particles go straight through. Therefore, which-way information is large. This makes the complementarity inequality violation very large. When a photon makes contact with a wire, it has two equally probable possible momentum states it can occupy. It can either go in the first or the second beam. The photon may take either state, so when it is detected, it's unknown which path it came from. So, which-way information is 0. This resolves the paradox as there is no violation of the complementarity inequality. Photons that do not interact with a wire go straight through, while photons that interact with a wire are equally likely to follow the path of either beam. This interaction that the photon has with a wire is mediated by the electromagnetic force through virtual particles.